Hi guys, my name is IBM and I am solving the last component of Physics 9702 paper 4. This is component 4.2. Remember I said component 4.1 is the same as component 4.3 for this October-November series, so I will not solve component 4.3. Without wasting time, I would like to take you to the question paper. So this is the question paper. You can download the question paper and follow through with the video. So it is 9702 and this is paper 4.2. The paper is 2 hours. I'll try to solve it as fast as possible. So I'll not look at the formula, I'll not look at the constants because I am very sure you are now used to the constants. So let's start. Question number 1, define the radian. Of course, if you recall that delta theta, that is the angular displacement, is the arc length over r, then it meant that if r is equal to the arc length, then delta theta would be equal to 1 radian. So it's like for a radian, the arc length is the same as the radius. So we shall define a radian as the angle subtended at the center of the circle when the arc length equals to the radius. That's what we mean by a radian, the angle subtended at the center of a circle when the arc length equals to the radius. The minute hand of a clock revolves at a constant angular velocity, angular speed, that is omega, around the face of the clock, completing one revolution every 1 hour. So the period is 1 hour. A small piece of modeling clay is attached to the hand with its center of gravity at a distance L from the fixed end of the hand as shown. Then calculate the angular speed omega. So we know that angular speed is simply 2 pi divided by the period, and the period is 2 pi divided by the time. The angular velocity is 2 pi divided by the period. The period is 1 hour, which is 1 times 3,600 to change it to seconds. So it is 2 pi divided by 3,600. So that is 1.75. 1.75 times 10 to the power of minus 3 radians per second, that is to 3 significant figures. During a time interval of 1,400 seconds, the center of gravity of the piece of modeling clay moves through a total distance of 0.4. So it means the arc length through which the center of gravity moves through is 0.44. Calculate the angle through which the minute hand moves in this time interval. Remember, I have just said we defined the angular displacement delta theta as the ratio of the arc length to the radius. So we want to find delta theta. We also notice we know the arc length, but we don't know the radius, so I'll not use that one. We also know that angular frequency or angular speed is equal to delta theta by delta t. This is the angular speed or angular velocity. Angular speed is the rate of change of the angular displacement, that is delta theta over delta t. So this means delta theta is going to be, so I'll not use this one here, but delta theta over delta t is going to be equal to omega times the time t. So this is going to be omega, which is 1.75 times 10 to the power of minus 3 times t, which is 1,400 seconds. So I'll just multiply this by 1,400. So this is 2.44 radians. Let me check with 1.75 exactly. 1.75 times 1400 times 1 exponent minus 3. So it is approximately 2.45. Okay, let me take 2.45. Okay, determine distance L. So to determine distance L now it becomes very easy since I now know that delta theta is equal to the arc length over the radius. So the radius, we have the arc length. The radius is going to, through which the mass is moving is the distance L. This is going to be delta S over L. So L is going to be the arc length or the distance through which the mass moves or the modeling clay moves divided by delta theta. And they said it moves through a distance of 0.44. So I would say this is 0.44 divided by delta theta, which is 2 point, I think this is 2.45. So 0.44 divided by the answer. So this is 0.1795 or 0.18. So L is 0.18 in meters. Then calculate the magnitude of the centripetal force. Centripetal acceleration. Of course, we know that centripetal force is mv squared over r, and centripetal, this is mass times centripetal acceleration. So it means the centripetal acceleration is simply v squared divided by r. And since we have, we know that v equals to omega r, so it means the centripetal acceleration is going to be omega squared r squared divided by r, which is omega squared times r. So it means the centripetal acceleration SC is going to be omega. Omega was 1.75. So I would say this is 1.75 times 10 to the power of minus 3, but this is squared. Then times r, which is the length L. R is L, so this will be times 0.18, because the length, the distance from the center, is the radius through which the modeling clay moves. So R is the same as L. So I'll just press my calculator. 1.75 exponent minus 3. Oh, this is squared times 0.18. So this is 5.51 times 10 to the power of minus 7. So 5.51 times 10 to the power of minus 7 meters per second. Use your answer in C Roman 3 to explain why the variation with the time of the magnitude of the force exerted by a minute hand on the piece of modeling clay is negligible as the minute hand undergoes one full revolution. So look at the centripetal acceleration. If we multiply this by the mass of the modeling clay, the centripetal acceleration is too small, which means the magnitude of the force is also going to be extremely small. The centripetal acceleration is very small. Compare this with acceleration due to gravity, which is 9.81. So the centripetal force is going to be too small. Also, okay, I think that is enough. I'll just simply say the centripetal acceleration is negligible compared with acceleration of free fall. If we compare this with the acceleration of free fall, which is 9.81 meters per second squared, then this centripetal acceleration of 5.51 is too small. And what is the effect? It means the resultant force is going to be negligible compared with the weight of the modeling clay. So it means the resultant force the resultant force is negligible. Is negligible compared with the weight of modeling clay. The resultant force is negligible compared with the weight of modeling clay. So this means the variation in the weight, the variation in the magnitude of the force is negligible. So the variation is negligible. Okay, because the centripetal acceleration is very small, it means the centripetal force is going to be very small compared to the weight. And therefore, the variation is going to be too small and negligible. Okay, question number 2, define gravitational potential at a point. Of course, this is for gravitational potential. Look at the mass. So the work done per unit mass. The work done per unit mass in moving a mass or a test mass from infinity to the point. That is the gravitational potential at that point. The moon may be considered to be an isolated uniform sphere of mass 7.3 times 10 to the power of 22 kilograms. Calculate the gravitational potential at the surface of the moon. So we know that gravitational potential is negative G capital M over R, where R is the distance from the center. So this is going to be negative 6.67 times 10 to the power of minus 11. That is a constant G. Then the mass is 7.3 times 10 to the power of 22. Then divide by the distance with the radius, which is 1.7 times 10 to the power 6 if you're on the surface. So we shall press the calculator. So of course the answer is going to be negative. The negative is not optional for gravitational potential. So it is 6.67 exponent minus 11 times 7.3 exponent 22. Then divide by 1.7 exponent 6. So this is giving me 2.86 times 10 to the power of, so 1, 2, 3, 4, 5, 6, power of 6. So since gravitational potential is the work done moving a unit mass, so it is work which is joules per unit mass, that is joules per kilogram. So the answer here is in joules per kilogram. So that is the gravitational potential, joules per kilogram. An isolated uniform spherical planet has gravitational potential phi at its surface. So at the surface, gravitational potential is phi. A particle of mass m is projected vertically upwards from the surface. The particle is given just enough kinetic energy to travel to an infinite distance away from the planet, escaping from the gravitational pull of the planet without any additional work being done onto it. Determine an expression in terms of m and phi. The gravitational potential, of course, by definition, if potential is work done, which is phi, then potential energy is potential times mass. So this is going to be m times phi. So this is going to be mass times phi. Remember, phi is minus, phi is a negative. Then show that the speed v at which the particle is projected upwards from the surface of the planet is given by that. Of course, if it reaches infinity, energy at infinity is going to be zero, but remember it has kinetic energy plus potential energy. And by concept, the sum of these two should be zero. If at infinity, potential energy is zero. So in that case, we know that kinetic energy is a half mv squared, and potential energy is going to be m times phi. This should be equal to zero. M cancels out, so I remain with a half times v squared plus phi equals to zero. So I make v the subject, so I'll have that v squared is equal to negative 2 phi, and when I find a square root, v is going to be the square root of negative 2 phi as required. Okay, the particle is moving upwards at the surface of the moon. Use your answer in A Roman 2 and expression in B Roman 2 to determine the minimum speed of the particle. So we are going to use the expression in A Roman 2, which was gravitational potential, and B Roman 2, which is V equals to negative root of phi. And we're going to use that to determine the minimum speed, okay? So V is equal to the square root of negative 2 times phi, that is from B Roman 2. And yet in in A Roman 2, we got phi as negative 2 point. Have negative 2.86, so I'll just substitute. So this is going to be the square root of negative 2 times negative 2.86 times 10 to the power of 6. So I'll just press my calculator. 2.86 exponent 6 times 2, root of the answer. So I have 2391.6. So this is 2392. Or I can write approximately 2400 meters per second to two significant figures. Hydrogen may be assumed to be an ideal gas. The mass of hydrogen molecule is 3.34 times 10 to the power minus 27 kilograms. Calculate the root mean square speed of a hydrogen molecule in a hydrogen gas that is at a temperature of 400. So of course we know that the average kinetic energy of a single molecule is equal to 3 over 2 times kT. This is a half. M mean square speed is equal to 3 over 2 times kT. So a half has cancelled out, so I will remain with the mass. Or I make the mean square speed the subject, so this will be 3 times Boltzmann's constant, which is 1.38. times 10 to the power of minus 23 times temperature, which is 400, divided by the mass, which is 3.34 times 10 to the power of minus 27. So I want the root mean square speed, so I'll find the square root of the answer. So 3 times 1.38 exponent minus 23 times 400 divided by open brackets 3.34 exponent minus 27. Then I find the square root. So this is 2227. 2227, or I will just write 2200 meters per second. So I have to find the square root. I have to find the square root of both sides. Then the surface of the moon reaches the temperature of approximately 400 Kelvin. When in direct sunlight, use answers in C and D. Suggest a reason why the moon does not have an atmosphere consisting of hydrogen. So look at this speed. This speed means that the molecules are most likely going to be, because the root mean square speed is like the average speed, it means molecules can have speeds higher than this. So if they have speeds higher than, some molecules have speeds higher than this, so most of them can always escape. So we can simply say the root the root mean square speed is an average value, or is an average so many molecules have speeds greater than the average. So many molecules have speeds greater than the root mean square. Many molecules have speeds greater than, let me just say, the average. So many molecules have speeds greater than, no, let me say, many molecules have speeds greater than the escape speed. Greater than the escape speed. Okay. Alternatively, I would have said there is a wide distribution of molecular speeds. There is a wide distribution of molecular speeds. That is around the root mean square. Around the root mean square value. There is a wide distribution of molecular speeds around the root mean square value. And what is the implication? So many molecules have speeds greater than the escape speed. So above and below the root mean square value, there are speeds, and many molecules would have speeds above the escape speed. Okay. State what is meant by internal energy. This is, of course, thermodynamics. Of course, internal energy is the sum of the random distribution, of the kinetic and potential energy of all the particles, that make up the system. So that is internal energy, the sum of the random distribution. We say random because the molecules are in a continuous random motion. So it's the sum of the random distribution of the kinetic and the potential energy of all the molecules. What is the spelling of random? The sum of the random distribution of the kinetic and potential energy of all the molecules or all the particles that make up the system. Use the first law of thermodynamics to explain what happens to internal energy of a spring when it is stretched. So that means V increases at a constant temperature within its elastic limit. So if it is within its elastic limit, then there is no energy dissipated as heat. So Q is zero, no thermal energy is transferred. So I'll simply say no thermal energy is transferred. Because we have not gone into plastic deformation, so there is no thermal energy transferred. I think transferred is double R, I think. No thermal energy is transferred. Okay. And let me look at the equation. Change in internal energy is Q plus W. So Q is 0, but W increases because the material is being stretched. So that means the internal energy is an increase. So work is done on the spring. Work is done on the spring, and if work is done on the spring, it increases the potential energy of the particles. So increasing the potential energy of the particles. Now that the particles are being stretched, so the potential energy is increased. And if potential energy part is increased, remember internal energy is equal to Ek plus E potential. The potential energy component is increased, so the internal energy increases. So internal energy increases. Then of a sample of water, it is water, it evaporates, so that means V increases. From a rain puddle on a hot day, it increases from a rain puddle on a hot day. Of course, the change in volume here is going to be very small. That means the work done is going to be very small on a hot day. So that means there is thermal energy transfer. There's some thermal energy transfer into the system, which is going to increase the internal energy. So thermal energy is transferred. Thermal energy is transferred to the water. Transferred to the water because it is a hot day. Work is done by the water against work is done by the water expanding against the atmosphere or against the atmosphere as it vaporizes. Work is done by the water expanding against the atmosphere as it vaporizes. So work is done by, and work done by is of course negative, but remember the work done is very small because the change in volume is going to be very small. If it is just evaporating from a rain pool on just a hot day, then the evaporation rate is very low. So the work is done by the water expanding against the atmosphere as it vaporizes, but then there will be more thermal energy transfer to the water than the work done. So we say more thermal energy is transferred to the water than the work done by the water. So when you look at change in internal energy is equal to Q plus W, this is very small compared to what is going into the system. So it means although this is going to be negative, it is a very small value compared to what is transferred to the water. So it means the internal energy increases. So more thermal energy is transferred to the water than work done by the water. And so internal energy increases. Okay, internal energy increases. An electron in a metal rod moves randomly about a mean position when an alternating voltage is applied to the ends of the rod. The mean position can be considered to oscillate with simple harmonic motion along the axis of the rod. The figure shows the variation with the time of the displacement of the mean position from the fixed point on the axis of the rod. Determine the amplitude of oscillation. So since this is oscillation, x naught is going to be equal to, so we get the peak to peak, peak to peak. So the peak to peak is this one here. It is this distance here. This is, the scale is 4 divided by 10, which is 0.4. So this is 7.2. So the peak to peak is going to be 7.2, but times 10 to the power of minus 15. Then we divide it by 2 to get just the maximum displacement from equilibrium, which is going to be, I think that is 3.6 times 10 to the power of minus 15. Then determine the angular frequency. So we know that omega is 2 pi divided by t. So this is 2 pi divided by the period. From the graph, the period is, if I consider starting from this point here up to this point here, so this is 0.15 and this is 0.35. So the period is 0.35 minus 0.15, which is 0.20. So the period is 0.20 times 10 to the power of, it is microseconds. 0.35 minus 0.15, that is 0.20 times 10 to the power of minus 6 seconds. This is the period, time for one cycle. So this is times 10 to the power of minus 6. So I'll check with my calculator. 2 pi divided by open bracket 0.2 exponent minus 6. So this is 3.14 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. So 3.14 times 10 to the power of 7. Then use your answer to show that the maximum drift speed V naught of the electron is given like that. So we know maximum speed is equal to omega times maximum displacement. The equation, the general equation is V is equal to plus or minus omega square root of x naught squared minus x squared. At maximum speed, x is 0. And when x is equal to 0, we come up with this equation here. We come up with this equation here when x is 0. So it means the maximum speed is going to be omega, which is 3.14 times 10 to the power of 7 times the maximum displacement, which is 3.6 times 10 to the power of minus 15. So 3.14 exponent 7 times 3.6 exponent minus 15. So that is 1.13 times 10 to the power of minus 17. 1.13 times 10 to the power of minus 7, not 17, meters per second, which is approximately 1.1 times 10 to the power of minus 7 meters per second as required. The rod has a cross-sectional area of 4.3 meters per centimeter squared and contains a number density of conduction free electrons. So this is small n. So this is area, small n. All of the conduction electrons in the rod may be assumed to be oscillating in phase with the same amplitude as the oscillation shown above. So the amplitude is the same. Use the information in A Roman 3 to calculate the magnitude I naught of the maximum current. So since we have small n, we have cross-sectional area, we have the speed, so we shall use I equaling to never. Current equals to never, that is from AS. So maximum current I naught is going to be N times the charge of the electrons times the maximum speed V naught times the cross-sectional area S. So I'll just substitute. N is 8.5 times 10 to the power of 28. The charge of an electron is 1.6 times 10 to the power of minus 19. Then times the drift speed. I think the speed is 1.13. 1.1, I'll just use 1.1 times 10 to the power of, is it minus 7? Yes, times 10 to the power of minus 7. Then times the cross-sectional area is 4.3, but I have to change it to meters. Meters squared, so I will say times 10 to the power of negative 4 to change it to meters. So I'll just press my calculator, 8.5 exponent 28 times 1.6 exponent minus 19 times 1.1 exponent minus 7 times 4.3 exponent minus 4. So this gives me 0.643. 0.643. Okay, let me just take 0.643 is fine. On the figure, sketch the variation of the current I in the rod with the time t between t equals to 0 to t equals to 0.4 microseconds. So, of course, at t equals to 0, the current is maximum, I is equal to I naught, because from this previous part, the rod has a cross-section area of that. All the conduction electron in the rod may be assumed to be oscillating in phase, and when they call the same with the same amplitude as the oscillation shown in the figure. Use the information to calculate the magnitude I naught of the maximum current. So the maximum current is that. So now sketch the variation of the current I in the rod with the time t from t equals to 0 to t equals to 0.4 microseconds. So let's check here. So at t equals to 0, okay, so here at t equals to 0, we have the displacement. At t equals to 0, the displacement is very close to 0. It is around, okay, let me see. When an alternating voltage is applied to the ends of the rod, the mean position can be considered to oscillate with simple harmonic motion. The figure shows the variation of the displacement with time t. Okay, the time the amplitude of the oscillation, the time the angular frequency used to show that the maximum drift speed, that is the drift speed. The rod has that cross-section and contains the number density that all of the conduction electrons in the rod may be assumed to be oscillating in phase So they are oscillating in phase with and with the same amplitude as the oscillation shown in the figure. They are in phase with the same amplitude, that is, okay, the oscillation with the same amplitude as the oscillation shown in the figure. Use the information to calculate the magnitude I naught of the maximum current. So we have seen the maximum current is that. Then sketch the variation of the current. Sketch the variation of the current I in the rod with the time t between t equals to 0 and t equals to 0 0.4. I will just use a simple equation. I is equal to I naught cos omega t, and I will use 0 point. I will be equal to 0.643 cos. I think omega was 3.14. So omega is 3.14. 3.14 times 10 to the power of 7, then times t. Okay, so it means when t is 0, I is equal to I naught. So the graph is going to be here. Then, of course, this is going to be sine curve. So when t is 1, 2, 3, 4, 5. Remember, 0.2 was the period. So when t is a quarter period, then it goes to 0. When t is half a period, it goes to negative maximum. When t is 3/4, it goes to 0. When t is 1 period, it goes back to maximum. When t is again another quarter, it goes to 0. Then it goes to maximum, back to 0. Then it goes to maximum. So this is going to be like this. Okay, as simple as that. So use your answer in A Roman 2 and B Roman 1 to determine an expression for I in terms of t. So this, I've just considered I is equal to I naught cos omega t, where I naught is 0.643 cos omega was 3.14 times 10 to the power of 7, then times t. So the equation they want here is 0.643 cos of 3.14 times 10 to the power of 7 t. Okay, so determine the root mean square current in the rod. Of course, we know that root mean square current is equal to I naught divided by the root of 2. The maximum current is 0.643 divided by the root of 2. So 0.643 divided by root of 2, that is 0.455 to 3 significant figures. State Coulomb's law. This is electric fields. We know that Coulomb's law, the electric force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of their separation. So that is electric force between 2-point charges. The electric force between 2-point charges is directly proportional to the product, is directly proportional to the product of the charges and inversely proportional inversely proportional to the square of their separation. Then two identical oil droplets are in a vacuum. The centers of the droplets are a distance of 3.8 times 10 to the power of minus 6 apart. The droplets have equal charge. They have equal charge and exert an electric force on each other. Determine the magnitude of charge on each droplet. So we have the force. We know that the force between two charges is the product of the charges. So it is Q times Q, which is Q squared, divided by 4 pi epsilon naught times the separation, which is x squared. That is according to Coulomb's law. So it means the charge, okay, I'll just substitute, but I just want to make Q the subject. So Q is going to be the square root of 4. Okay, let me make this short for now. Q is going to be the square root of F times 4 pi epsilon naught x squared, which is going to be the square root of F. F is 6.3 times 10 to the power of minus 17 times 4 pi. Then times epsilon is 8.85 times 10 to the power of minus 12. And times x. X is 3.8 times 10 to the power of minus 6. 3.8 times 10 to the power of minus 6. And this is going to be squared. So I'll just press my calculator. 6.3 exponent minus 17 times 4 pi times 8.85 exponent minus 12 times 3.8 exponent minus 6, but this is squared. So I'm getting 1 point. Press the calculator. Let me check it again. So I have 6.3 exponent minus, okay, let me just check the square root first. Square root of the answer, 3.18, okay. So Q is 3.18 times 10 to the power of minus 19. Okay, so it is 3.18 times 10 to the power of negative 19, which is approximately 3.2. One of the oil droplets in B is now placed between two horizontal microplates. Now, first of all, this is at a high potential, this is at lower potential, and the weight. So the weight is acting vertically downwards, mg. To balance this in between, there must be a force, the electric force, which must be vertically upwards. And if up is positive, then this charge must be negative for the force to be vertically upwards. So let's see the question. PD of 1200 volts is applied between the plates, with the top plate at the high potential and the oil droplet is stationary and in equilibrium. State the sign of the charge on the oil droplet. So we have already established that the oil droplet must be negative. Why should it be negative? Note that the upper plate is positive, the bottom plate is negative. There is a force acting on the oil drop downwards due to its weight. To balance the weight, the electric force must be acting upwards. The electric force acts in the for a positively charged particle, the electric force acts in the direction towards the negative plate. But if the electric force is acting towards the positive plate, then the charge must be a negative charge. That's why I'm saying this is negative. Then on the figure, draw 4 lines to represent the electric field between the plates. So you must draw this. This is a uniform field. So you must draw equally spaced field lines. So I'll try to make them equally spaced field lines. Okay, so these should be equally spaced because this is a uniform field and this points vertically downwards. Okay. Then the distance between the plates is 5.2 centimeters. Determine the mass of the oil drop. So of course, the electric field is the electric force is balancing with the weight. So we know that the force due to gravity is balancing with the force due to the electric field. So I'll say mg is equal to the force due to the electric field is given by charge times the electric field strength. And we don't know the electric field strength, but at least we know that E is also equal to V over D, where D is the distance between the two plates, which has been given as 5.2. Potential difference is 1,200 volts. So I'll simply say the mass, mg, is going to be Q times V over D. So I'll just make m the subject and substitute. So the mass is going to be the charge, which is 3.18, I think, times 10 to the power of negative 19 times Q. So that was the charge. Then V is 1,200 divided by D. D is 0. I think it was 5.2 centimeters, which is 0.052 in meters. Then times G. I'm making M the subject. And G is 9.81. This equation means M is equal to Q V over G times D. So I'll press my calculator. 3.18 exponent negative 19 times 1,200 divided by 0.052 times 9.81. So this is 7.48 times 10 to the power of minus 16 in kilograms. A capacitor C is charged so that the potential difference V across the terminals is 80 volts. Remember, when a capacitor is fully charged, the PD across it is the PD across the power supply. The switch is initially opened. The switch is closed at time t equals to 0. The figure shows the variation of V with the charge Q on the plates of the capacitor C as the capacitor discharges. Show that the energy stored in the capacitor C at time t equals to 0 is 1.8 millijoules. So of course the energy stored is going to be, because this is V against Q, the energy stored is equal to a half QV, or it is a half CV squared, which is the area under the graph. So the energy stored is equal to the area under the graph. So this is a half Q times V. So this is going to be a half times Q, which is, I think it is in between this box and this is, the scale here is 200 divided by 10, which is 20. So this is 20, 40, 50, so that is 450. So Q is 450 times V, when it is fully charged, V is equal to 8. So this is going to give us, oh, this is micro coulombs. So I have to say times 10 to the power of minus 6. then times 8. So when I press my calculator, I have 0.5 times 450 times, 450 exponent minus 6. I multiply this by 8, and it gives me 1.8 times 10 to the power of minus 3, which is the same as 1.8 millijoules. Then determine the capacitance of a capacitor C. Give a unit with your answer. Of course, we know by definition, capacitance is equal to Q over V. So if it is fully charged, Q is 450 times 10 to the power of minus 6 divided by 8.0. So 450 exponent minus 6 divided by 8, that is 5.63 times 10 to the power of minus 5. Of course, the units of capacitance is the farad. That is farads. Alternatively, you could use energy, as energy equals to a half CV squared. If the energy is 1.8 times 10 to the power of minus 3, this is equal to a half times capacitance times PD, which is 8 squared. We can check this with our calculator. 2 times 1.8 exponent minus 3. Then I divide by 8 squared. Then I find, okay, so that is the same thing. When I make C the subject, this gives me C as the same answer. The figure shows the variation with T of negative ln of V over 8.0 V. Show that when T is equal to 1 time second, the value of negative ln V over 8.0 V is equal to 1.0. So remember, the equation of discharge for a capacitor is given as V equals to V naught e power negative T over RC, where tau equals to RC. This is called a time constant. This is the time constant. But they are saying when T is equal to 1 time constant. So I want you to note that V is equal to V naught e power negative T over tau. And at 1 time constant, we know that T is going to be equal to tau. At 1 time constant, T, the time T is going to be equal to tau. And of course, V naught from at 1 time constant, then V naught, we started with 8, I think. So V naught was equal to 8.0 volts when it is fully charged. Okay, let's now just substitute in the equation. The V is not known, but the initial V is 8.0. This is going to be equal to E power negative at 1 time constant. Then T is going to be tau. At 1 time constant, T is going to be tau, so this is going to be power negative 1. And when I press my calculator to say 8 times E power negative 1. No, I think this is wrong mathematics. I have to introduce ln. So I'll say ln of V over 8.0 is going to be negative 1 times E. So when I take the negative the other side, it means negative ln of V over 8.0 is equal to 1.0, because I want us to show this. So I think that is fine. At 1 time constant, when T is equal to tau, then V naught, and V naught is equal to 8.0. I think that is true. Then determine the time constant tau of the circuit in the figure. Okay. So remember that ln, negative ln of V over 8.0 is equal to 1.0. And let's look at this. So for that, when negative V over 8.0, ln of V over 8.0 is equal to 1, what is the time constant here? So when this is 1, then this is going to be this value here, which is, this is 3.2. So it means t, which is equal to tau, is equal to 3.2 seconds. So the question is determine the time constant. Remember, for one time constant, small letter t is equal to tau. So this is going to be 3.2 seconds. Then calculate the resistance. Since time constant is equal to R times C, then R is equal to tau divided by C. So which is going to be 3.2 divided by the capacitance. I think the capacitance is 5.63. So divide by 5.63 times 10 to the power of minus 5. So I'll press the calculator. 3.2 divided by 5.63 exponent minus 5. So this is 5.68 times 10 to the power of 4. 5.68 times 10 to the power of, that is power 4 ohms. A hollow probe containing a thin slice of semiconducting material is placed in a uniform magnetic field of flux density B. It is uniform. The largest faces of the slice are perpendicular to the magnetic field as shown. Okay, so you have a current which is perpendicular to the magnetic field. So it means the semiconductor slice must be experiencing a force. The thickness X of the slice is 1.8 millimeters. The number density, that is N, is 1.5 times 10 to the power of 16 per meters cubed. A constant current 5.4 amperes passed through the slice between the shaded faces. The whole voltage VH that is developed between the terminals PQ is recorded. Okay. The figure shows the variation with the time t of B. Okay. Show that when B is equal to 4.0 times 10 to the power of minus 16, the magnitude of VH is equal to that. So we know that the whole voltage VH is directly proportional to B and is given by BI divided by NTQ. You studied this in magnetic fields. B is 4.0 times 10 to the power of minus 6. The current was, I think, 5.4. The current is 5.4. The number density was given as 1.5 times 10 to the power of, is it 16? Yes. Then thickness, the thickness is 1.80 millimeters times 10 to the power of minus 3 to change it to meters. Then the charge, these are electrons, so it is 1.6 times 10 to the power of negative 19. Let's just check with the calculator. 4 times 5.4 exponent minus 6. I just changed the position of the power, but it's the same thing. Then divide by 1.5 exponent 16, 1.8 exponent minus 3, 1.6 exponent minus 19. So this is giving me 5. Exactly 5.0 volts. On the figure, sketch the variation of VH with T between T equals to 0 and T equals to 0.5. 0.08. So this is very easy. Remember, VH is directly proportional to B. VH is directly proportional to B. So let's check. When B is 0, VH must be 0. When B reaches its maximum value at 0.02 seconds, B is maximum. That means VH is going to be 5. So here this is going to be 5. And when B remains constant, V also remains constant. Then B at 0.05, B is halved. That means VH is also going to be half. So it will be 2.5. Then it becomes constant, as simple as that. So let's sketch. When at equals to 0, VH is going to be 0. Then at equals 0.05, VH becomes maximum, which is 5. 5 is 1, 2.5. 5 is here. And then it remains constant between that time and 0.04. Then B, remember I'm considering VH is directly proportional to B. When B halves, it became 2. VH should also be half of the maximum, so it becomes 2.5. So at this time here, 2.5, this is 2.2, 0.4, 0.5. So this is 2.5 here. Then it becomes constant. So I'll just now draw with the ruler. Let me increase the thickness. Okay, so that is going to be our graph. VH is directly proportional to B. So the pattern, the shape is the same. Only that the values are the ones which change. This one goes up to 2.25, and here it will be at 5. That is the maximum. Okay. The whole probe in A is replaced with a small flat coil that has 3,000 tons. The cross-sectional area of the coil is 3.4 times 10 power minus 4 meters squared. The plane of the coil is perpendicular to the magnetic field. The EMF induced between the terminals of the coil is recorded as B varies as shown in the figure 7.2. Show that the magnitude of E at time t equals to 0.01 seconds is 2.0. Time t equals 0.01. So it is here, it is a straight line. So because the rate of change of magnetic field is constant with the time, the induced EMF is constant anywhere on the straight line. So it is going to be a constant value. I'll try to reduce the thickness first. So we know that the EMF is equal to the rate of change. The EMF is the rate of change of the magnetic flux linkage. So the EMF is going to be, of course, the rate of change of magnetic flux linkage, or the EMF is equal to NBA divided by T. That is the EMF, because flux is equal to BA. If it is a coil, we multiply this by the number of turns. So this is going to be NA times the change in the magnetic field with time. So this is going to be the same as NA maybe times the gradient of that graph. So N number of turns is 3,000 times the cross-sectional area, which is 3.4 times 10 to the power of minus 4 then times the gradient. Let's check the gradient. So it is 4 minus 0 over 0.2 minus 0. That is the gradient. So it is 4, which is simply 4 times 10 to the power of minus 6 divided by 0.020. So I'll just press my calculator to verify. So we have 3000 times 3.4 exponent minus 4, then times 4 exponent minus 6 divided by 0.02, which is 2.04 times 10 to the power of minus 4. 2.04 times 10 to the power of minus 4, which is approximately 2.0 times 10 to the power of minus 4 volts. Sketch the variation of E for the time between time t equals to 0 and t equals 0.08. So the maximum value of E, okay, let's check here. Let's check the gradients. So this gradient is 4 divided by 0.2, and this gradient is 4 minus 2, which is 2 divided by 0.01, I think. 0.01, is it the same? 4 divided by 0.2, sorry, 4 divided by 0.02, 4 divided by 0.02, okay, that is 200, and the other one is 2 divided by 0.01. So the gradient is the same. So it means the EMF is the same in magnitude. So this is same gradient. The EMF is the same in magnitude, but this gradient is positive, the other gradient is negative. Of course, I'm leaving out the 10 power negative 6, the 10 power negative 6. On the left, the gradient of the line is positive. On the right, the gradient of the line is negative, but the magnitude is the same. So they should be in opposite direction. The induced EMF is always in the opposite direction. So for the first 0.02 seconds, the EMF is constant, and it is 2.0 times 10 to the power of minus 4. Then for between 0.04 and 0.05, the induced EMF is 2, negative 2. It is in the opposite direction. Where the line is horizontal for B, where remember EMF is directly proportional to the rate of change of magnetic flux. Where magnetic field is not changing, the induced EMF is 0. So this part here we have 0, and this other part here we also have 0. So if I was to do this graph, you can use a ruler. I will use a free hand. So this is a horizontal line. I will draw a step here. I will draw a step here. I will draw a step here. So that will be the graph. The EMF is the same in magnitude because the gradients were the same on both sides. But the one gradient is positive, another gradient is negative, so the EMFs cannot be on the same side of the graph. So that means this is going to be the correct graph. State what is meant by a photon. Of course, we now know that a photon is a packet of energy, of electromagnetic radiation. A packet of energy of electromagnetic radiation is what we call a photon. When the surface of a metal plate is illuminated with electromagnetic radiation, electrons are sometimes emitted from the metal. State the name of the phenomenon. Of course, this phenomenon is called photoelectric effect or photoelectric emission. It is observed that the phenomenon occurs only when the frequency of the electromagnetic radiation is greater than a certain minimum value regardless of the intensity of the radiation. Explain how this observation provides evidence for the existence of photons. Okay, there is a minimum frequency below which no electromagnetic radiation is emitted, which means electrons need a minimum energy to escape, because the energy of the frequency determines the energy of the photon. So it means the electron needs a minimum energy. An electron will need a minimum energy to escape. And this energy must be, of course, this energy must be absorbed in packets that are related to frequency. The energy of these packets is related to frequency. The energy must be absorbed in packets that are related to the frequency. Remember, the energy is equal to hf. The energy must be absorbed in packets that are related to frequency. And of course, the intensity only relates to the number of packets. Intensity, because I see intensity here, regardless of the intensity. Intensity only relates to the number of packets or number of photons, not their energy, not energy in the packets. So the intensity does not determine the energy in the packets, and therefore, and of course we know that the electrons absorb only, an electron absorbs only a single whole packet. An electron absorbs only a single, an electron absorbs only a single whole packet, not in halves. We mentioned that you must have mentioned in your class that is a one-to-one interaction. An electron absorbs a photon as a whole. This photon should have energy which is equivalent to the difference between two energy levels. Okay. So the figure shows the variation of the maximum kinetic energy of the emitted electrons in B with the frequency of the incident radiation. State the name of the quantity represented by the gradient. So this is maximum kinetic energy against frequency. Of course, this is going to be F naught, threshold frequency. And if we extend this to the y-intercept, we know that kinetic energy or energy of the photon, which is HF, is equal to H F naught, which is the work function, plus, so this is the work function, plus the maximum kinetic energy, EK. So when I make EK the subject or Emax the subject, Emax is going to be HF minus phi. When I compare this with y equals to mx plus c, it means that the gradient is Planck's constant, and the y-intercept is the negative work function. So the gradient of the line is Planck constant. The gradient is Planck's constant, and the y-intercept is going to be the minus work function energy. So I've just written this using the equation of a straight line. If I know energy of a photon is the work function phi plus kinetic energy Emax. Because on the y-axis I have Emax, on the x-axis I have F, I just made Emax the subject. And then when I compare with y is equal to mx plus c, I notice that m is h and plus c is negative 5, which is negative work function. Fluorine is a radioactive nuclide that is used as a tracer in positron emission tomography, which is a PET scan. This is the new scan state by a tracer. Of course, we know that a tracer is a material introduced into the body and absorbed by those tissues which are being studied. So it is absorbed by the tissues, by the tissue or by the tissues which are being studied. That is the tracer. It is a material introduced into the body to aid into studying a certain part of the body. That is what we call a tracer. State the symbol of the particle that is represented by X and values of P, Q, and R. Of course, this is going to be this X is going. This is oxygen, so this is going to be 16. Sorry, this is going to be 18, not 16. This is going to be positron, which is beta plus. So it is 0, 1. So the other one is 18. So X is beta plus. They said symbol, so it is beta plus. Q is 0 and P is 1. Then R is 18. Explain how the reactive decay of fluorine results in the emission from the gamma ray photons detected during a test scan. Of course, the emitted photons release electrons and protons. Their total mass becomes energy and it is detected as gamma ray photons. So the emitted positrons meet electrons and annihilate. They annihilate. So the mass of these particles becomes energy in form of gamma ray photons. The mass of these particles becomes energy of gamma ray photons or energy of gamma photons detected outside the body. Okay, so the gamma ray photons come from the patient and they are detected by the gamma ray camera outside the body. Then explain how the detection of the gamma ray photons is used to produce an image of the tissue being studied. Of course, we just look at the arrival time. Processing the arrival time can be used to build up an image of the tracer concentration in the tissue. So we can say arrival times. The arrival times of photons are detected. Arrival times of photons are detected, processed, and an image. And an image is built up. An image is built up and an image is built up. Let me say an image built, and an image is built up of tracer concentration in the tissue. So an image is built up or is generated from to show the tracer concentration in the tissue for a particular part of the body. Then the half-life of fluorine 18 is T. A patient is injected with an amount of substance N of fluorine. Determine an expression for the initial value R naught of the rate R of the production of gamma ray photons by the tracer in terms of N, T, and Avogadro's number Na. So we know that activity is equal to lambda times N. And we also know that the decay constant lambda is equal to ln of 2 divided by half-life T. They have told us the half-life is T. So the activity, the initial value is R naught. So I'll simply say R naught is equal to ln of 2 over T, then times N. But I also know that number of moles or number, a patient is injected with amount of substance, that is number of moles. So I know that number of moles is N over Avogadro's number Na. So this means that capital N is going to be small n times Avogadro's number Na. So it means R naught is going to be ln of 2 over T times small n times Na. Okay, so determine an expression for initial value R naught of the rate R of the production of gamma ray photons by the tracer in terms of N, T, and the Avogadro constant Na. A patient is injected with an amount of substance N of fluorine. So I have NNA divided by T. Oh, remember, for every reaction, there are always two gamma ray photons. So let me just write here a statement that two photons are produced from each decay. Two photons are produced from each decay. So for one photon, this is what we have. So R naught is going to be equal to twice ln of 2 times NNA divided by T. So this is twice ln of 2 times NNA divided by T. Okay, so two photons are produced from each decay, so R naught is going to be twice that. So I just multiply this by 2. So the answer is going to be that. Then on the figure, scale the variation with time t of R. So of course this is going to follow R is going to be equal to R naught e power negative lambda t. That is an exponential curve. So at t equals to 0, we start with R naught. At t equals to 0, R is equal to R naught. Then at t equals to a half-life, which is capital T, R should be R naught over 2. R naught over 2, I think it is this one. Then at t equals to twice T, this was capital T. So R is again half R naught, which is going to be R naught over 4. So this is twice T. So this is the point. So I just divide this, I just sketch this curve. Okay, so that will be the curve. It goes through this point, and then that point, a quarter. So that is the curve. That was a simple question. And lastly, state Wayne's displacement law. Of course, this is astronomy and cosmology. Wayne's displacement. We know that the wavelength at which maximum intensity occurs, or at which maximum intensity of radiation is emitted, is inversely proportional to the absolute temperature. So the wavelength at which maximum intensity of radiation is emitted. The wavelength at which maximum intensity of radiation is emitted is inversely proportional to the absolute, or to the thermodynamic temperature, to the absolute temperature. In other words, the temperature is in Kelvin units. Lambda is inversely proportional to T. Lambda max is inversely proportional to T. That is Kelvin. That is Wayne's displacement law. The temperature is thermodynamic. In other words, it is in Kelvin units. State what is meant by a standard candle. Of course, we know that a standard candle is an astronomical object whose luminosity is known. Astronomical object. An astronomical object is an object in space. An astronomical object of known luminosity. An astronomical object of a known luminosity is what we call a standard candle. State the reason why the radiation from the star is redshifted. A cosmology student observes the electromagnetic radiation received from a star in a galaxy. The student uses Wayne's displacement law to estimate the surface temperature of the star. A standard candle to estimate the distance. So he's using a standard candle to estimate the distance. So in other words, he's using F is equal to L over 4 pi d squared. Wayne's displacement law is using lambda max is inversely proportional to temperature. So standard candle to estimate the distance, and Stefan Boltzmann's law to estimate the radius of the star. Stefan Boltzmann's law, L is going to be 4 pi sigma r squared T power 4. That is Stefan Boltzmann's law. So state the reason why the radiation from the star is redshifted. So redshifted means the wavelength is greater, and a longer wavelength means the star in the galaxy which is moving out from the student. So the star is in a galaxy which is moving away from the student. That is why it is redshifted. Redshifted means the wavelength is longer wavelength. Okay. Then true values of the quantities observed or estimated are those that are corrected to allow for redshift. However, the student does not correct for redshift. Okay. By placing one tick in each row, complete the table to indicate how the observations and estimates made by the student compare with the true values. Wavelength. We know that wavelength is related by this. Lambda is inversely proportional to the temperature. So because there is redshift and the student did not correct for redshift, it means the wavelength he must have got is going to be too high. The wavelength the true values of these quantities observed or estimated are those that are corrected to allow for redshift. In other words, to remove the redshift. So because the student did not remove the redshift, it means the wavelength the student observed is too high. So the answer is going to be too high. Then temperature, because the wavelength is too high, it means the temperature is going to be too low. So I'll put here the T. Then distance. For distance, the student used the standard candle. That is F is equal to L over 4 pi d squared. So if the luminosity is constant and the student is using the standard candle, the radiant flux intensity is also constant, so it means the distance is not being affected, so D is the same. From F equals to L over 4 pi d squared, this is constant, this is known, because for standard candle, the luminosity is known, and the radiant flux intensity is of course measured from the Earth, so the distance D is going to be the same. Then using Stefan Boltzmann's law, that is L is equal to 4 pi sigma r squared T power 4. 4 pi and sigma, these ones are constants. The luminosity is known. So it means r squared is inversely proportional to T power 4. And remember, the temperature was too low. That means the radius is going to be too high because they are inversely proportional. R is, when I remove the square roots, R is inversely proportional to T squared. When the temperature is too low, it means the radius is going to be too high. So this will be the tick will be there. And I think that marks the end of May-June paper 4.2. I think I've tried to be very fast. So if you have anything you want me to clarify, you can always write me a message. You can write a comment. For now, until next time, bye-bye.